Okay. All right, well, this is Perez, and she's been my graduate student for a number of years now, helped me out a great deal. Is a strong advocate of solar, has helped me a lot with the, we have an engineering research center with ASU and Caltech and a number of other universities. She's been on the Student Leadership Council, the head of that actually, and also had an internship at NREL, which was very beneficial both to her and to me, because we ended up getting a research grant as a result of that, and this work is an outgrowth of that effort. So.
Thank you everybody for being here. Just so you know, we have a full house here, and we also have 27 people online joining us from various parts of the country and other countries. So thank you everybody for joining. I have some acknowledgements at the end. But today I'm going to give my defense of my dissertation project, which is on bifacial solar panels, system design, modeling, and performance. And I'm going to walk you through all of this material just so that you understand this complex title. But the first thing that I want to say is that bifacial means that type of solar panels that you can see through. Okay? Of course it doesn't move. Technology work for me. There we go. Excellent. So an overview of how we're going to go today. We're first going to give some motivation and background, some background topics so that we are all speaking the same terms. And we're going to look a little bit into the economy and how this affects what we as engineers must achieve under modeling. Then we're going to talk a little bit about irradiance modeling. Irradiance is light. And as it reaches our solar panels, there are various models that I am going to talk and present some enhancements that I've done or helped do to these models. Then we're going to do a comparison, and finally I'm going to present a test bed. That is an experiment, a real experiment. The final topic is on yield modeling. So on performance modeling, we talk about bifacial gain, that is how much we get of benefit from using bifacials. And I'll also present some results from an array system. So our goal overall, and this is like taking a big step back, is to protect the environment. That's why everybody that works in solar is there on the environment. And I really like this picture, and I chose it as a background because this is the first time that we as humans saw the Earth, the little bubble. And that's when all of the environmental movement started, when we realized how important it was to protect our environment. So our goal is to protect it. And what we do, people working on solar, is we develop clean, renewable energy technologies that are competitive with fossil fuels. Fossil fuels is gas, natural gas, all of that. And we want to improve the efficiency and the cost of solar energy so that at some point we are just using natural, clean energy. How we do it, or how I do it, it's with bifacial photovoltaic technology. Photovoltaic is solar panels converting energy. And the purpose of this research that I'm presenting is, am I blocking people's? Yes. To develop and demonstrate techniques that will show, that will allow us to model and predict what the output will be of these technologies. So going into a little bit of background, so that we're all talking the same language, because I know we are not all from the same background. We have solar cells. Solar cells make up modules or solar panels. Solar panels get put into arrays to produce electricity. These are two examples. One is a field. The other one is a rooftop of a commercial building. And we actually also have here monofacial and bifacial technologies. And bear with me 2 more slides, and I will go into this in detail. But so we have arrays, right? When we mount the solar panels, we can mount them on landscape, on portrait. We can put them 2 up, 3 up. That's how we denominate it, how we are putting it. And this, for the purpose of our research, we just care about the overall collector width. That's what we're going to normalize all our measurements because it is a scalable issue. We have fixed mounting, and we also have tracking mounting with a little animation there. The tracking means single axis tracking means that it's following the sun as it moves through the day. So they rotate. You may have seen this if you drive around towards California. And when you have the rotating tracker, then your height to the ground, it's going to be constantly changing, right? So we usually define this distance based on the hub height or the axis height. Now, the difference between the monofacial and bifacial, they're pretty much the same cells. There's some difference on the procedure though, because we don't use a back contact on the solar cell so that we can get light through. So they look pretty much the same from the front and the back. We have monofacials usually have frame. Bifacials may or may not have a frame. They have a glass layer, then they have an EVA or polymer to keep everything packed nicely. And they have a back sheet, which is usually white on most monofacials. And on the bifacials, we have just glass. So it's like a symmetric, more or less. Looking a little bit more into the cell structure, it can be a P-type or N-type wafer for those that are a little bit more into the semiconductor. But the main difference, again, is that we have front contacts on both, and on bifacials, we have rear contacts instead of using the whole back surface as a contact.
I have a question.
Yes.
And this is nice clarity. So with bifacial and monofacial, we use the same amount of silicon.
Yes.
So that's good. Okay, because I didn't see that at the beginning. So that's good. Okay, because I was thinking about the cost if you had an extra layer of silicon. So that's good. Okay.
It's usually the same thickness. Yeah.
Okay.
The issue is if it was thinner or something, less light will be absorbed and will just go through. The monofacials provide the back sheet that reflects back, so you have double the path light to absorb. So definitely I don't think they will go thinner, but I don't know a lot of this part. So, and for those of us that are electrical engineers that deal with solar cells, this is the electrical diagram or the model that we use to predict what the output will be when we have a particular source of input of light. The model is a current source, a diode, and shunt and series resistance. The equations are there. And as you can see on the bifacial, we have an extra current source for the rear. But current source add up and they're on parallel. So we treat it basically as the same source. So we can use the same equations. We just add up the input of irradiance from the front and the back. And that's how we deal electrically to model this. One thing, though, that is different is that the back side is not always as good at converting the light as the front side. Or when you make a module, you might block some of the light with the frame or the electronics on the back. So we define a term that's called the bifaciality factor. Yes, bifaciality factor, which is the minimum of the maximum power or the maximum current from the back compared to the front. These values are typically 60% to 90% commercially. On the lab, they're as high as 99%. But so that means that the back is going to produce just slightly lower. And why are we proposing bifacials? And the main thing about monofacials is that they have this back sheet, right? Depending on how we mount them, they will see the direct light from the sun, and they will see only partial part of the diffuse light. As we all know, like we have a lot of light coming from the sun directly, but we also have diffuse content that is scattered around. And that is something that the bifacial modules can take advantage of. They will see all of that light. They will see light reflected from the ground, from objects, from the clouds. And how much is that benefit? This map shows the United States and all of the weather stations that are available on the National Renewable Energy Database. And it shows a comparison of the diffuse to direct ratio for all cities. So we can see there is a lot of places that have a lot of diffuse content. Those are all of those blue areas. And even on the southwest here, where we have like very sunny days, there is a 20% content of diffuse that we could take advantage of if we use this technology. So let's take this is the formula slide. I'm going to try to explain this nice and easy. So efficiency on any system is always the output over the input, right? Other case, our output is the yield or the energy that we are producing. And the input is the irradiance, which we name E. Irradiance with E, like elephant, with E. On monofacial and bifacial, we said, okay, so the irradiance input is just the front. On bifacial, the input is the front plus the back. But the back is affected by that bifaciality factor. It's slightly reduced, yeah? So good so far? I see nods, that's good. Now, if we want to say, okay, how much then is our bifacial gain due to the extra irradiance, we can just use the rear irradiance divided by the front irradiance and get the percentage of that, and that is the gain, right? So if we have a place where there is 3% diffuse irradiance, there is 300 watt per meter square getting to the back of the panel compared to 1,000 watt per meter square getting to the front of the back of the panel. To the front of the panel, then we have that bifacial gain on irradiance. Now, we could also calculate a bifacial gain with the output, right? Compare the output of a monofacial and of a bifacial panel. Yeah, practical? Yeah, that will tell you how much. We'll come back to this formula a little bit later. So let's talk about the economics. How good is this extra energy yield? So in order to compare systems, solar, geothermal, gas, anything that we want to be able to produce energy, we use a term that's called the LCOE, the levelized cost of energy. And on this term, we have on the top, the total life cycle cost. That is how much money goes into this project, how much initial investment you have, that's a CAPEX, how much operation and maintenance you have, that's the OPEX, and how much years you expect your system to go, and also some discount rates, some economic terms there that you're predicting for your project. And on the bottom, you have your total lifetime energy. That is how much energy you're predicting to produce over the 25 years, 30 years that your system is going to be alive, which is the common warranty for solar projects. Okay. In general, we want a low LCOE. Yeah, the lower, the better, because utilities want to sell the electricity, right? So that means more gains. This plot shows a comparison. This is from ARENA database. This shows a comparison of the different technologies of producing electricity compared to fossil fuels. So that green area at the bottom is the cost of fossil fuel range. And we have years, 2010 and 2017 comparison. And in yellow, we have the solar photovoltaic. And we can see that most of the projects, the LCOE now, it's comparable to fossil fuels or even below on many cases. And that is good. That is what we want. We want to bring solar all the way here or even below. Now, is bifacial technology going to help us to do that? It actually is. There's predictions that this is the case. This plot here shows some technologies that people are researching to implement on the silicon, making silicon. Some are like doing curveless wafers or frameless glass modules. So many different variations of how you make the module, how you make the solar panel. And bifacials is very easy, or it's very close to being adopted. The years to adoption is 2 years, 1 year. We're already seeing fields of this. And if the improvement is 5 or 10%, the reduction to the LCOE, this is how much the LCOE will be reduced. It's a significant number. So this position here, it's very good. This makes it like a no-brainer. Yes, we should aim for this. However, here is a news from January, so a couple months ago. There was this project. Saudi Arabia wanted to build a solar panel plant. So they called for people to put in projects. Yeah. So people came up with projects, and there was this French company that said, I want to do bifacial panels on single axis tracking. And they calculated their LCOE with their system that they were going to build, and it was pretty low. It was actually the lowest by 25%. However, the person that wanted to build this project said, I'm actually going to go with the guys that are a little bit more expensive because their technology is proven. And this brings us to the main hurdle that we are trying to do. On the LCOE, all of the parameters are important, but the yield itself it's the thing that makes the most change, the most impact on the LCOE. So we don't know that yield very well, that LCOE might be brown. And if you're going to invest on a 200 megawatt plant or bigger, that's a ton of millions. So you want to have very low risk. You want to know, okay, this is going to perform like it should perform. And this will increase the bankability of bifacials. Bankability means how profitable they are. The people will want to buy in. It makes sense to invest on them. So to do all of this, we need more accuracy. We need to prove this technology better. So let's take a little bit of a look at accuracy. And just as a reminder, we have here the difference between accuracy and precision. Precision is when we have a lot of measurements that are close to each other, right? So this is precise. But accuracy is when the measurements are on the bull's eye, when they are on reality, when they reflect what's real. Commonly for due diligence, that is for the paperwork and the proving that the system is going to work, people here in the US use engineers and project managers use PVsyst. PVsyst is a software that models the weather, the panels, the electric performance, the inverter, so all of the losses on the system. And in general, this is kind of hard. This number was very hard to find in literature, but it seems that it's more or less acceptable that it's 1% accurate between the predicted and the outcome. They do suggest that you provide your weather files that you use to model so they be updated as warranty, but so that's plus minus 1% with the reality. SunPower, a particular company, also had a presentation where they claimed they had 0.86% on their models versus their test. But again, these are, they were using their own models. That's not available to the public. PVsyst is available for purchase. And Sandia National Labs did a study too of this accuracy needed. And they actually broke this down into two parts, which we're gonna study in a little bit. One is a radiation model, that is the sun, how you model the sun in the sky. And they found that there's a 2% already of inaccuracy on that part. And then at the end of the performance model, that adds up to a total of 3%. But this is all for monofacials. Where are we with bifacials? Well, and let's make a little, obviously, a little step here onto a model. When we have a model, this yellow box, white box, we want to make something that's similar to reality, right? So we have a sun or a radiation model, or we sometimes use typical meteorological data, which is data that has been captured for a long time and then statistically evaluated to represent the weather on the site. So they might say, oh, it always rains on November 6th, my birthday, or something like that, right? So they have that. And those are the input to an irradiance model for the front, which are very well studied now for monofacials, or the rear if we're doing bifacials. And that will predict the output of the system, right? Now, this output from the irradiance, we can also feed it into a module model. So the electrical model that we're using with whatever parameters we're using for the panel. And that will tell us what the output is, how much energy we're producing. And that we can compare to the output. Yeah. Now, in reality, we want to actually, to get the accuracy, we want to do the experiment or prove it with field data. So we have to set up weather instruments. We have to set up, if we want to prove irradiance, we have to set up front and rear radiance measurement. And we have to set up also, or measure the output. Yeah. And the weather instrument, then we feed that information into the irradiance model. And so we can validate or compare how close we are or not in our model at these two stages. Yeah. Yes.
So the performance modeling, is that based on manufacturer specifications for module performance, or what is performance modeling?
Yes. So the performance modeling, it's using the single diode model, for the module. The issue here that adds a lot of uncertainty is that the specifications that we use are usually from the producer, sometimes from national labs, or I guess those are, and they usually test 1 or 2 modules, and we assume that that is the same behavior that all of the other modules are going to have. So we get parameters for and we assume that they're going to behave like that on the field, even if it's like the 100 production after the first 2 that were.
So on your previous slide where you had 2% radiation accuracy and 3% performance accuracy, so there's basically only a 1% difference between specified values and actual performance.
Yeah.
Does that is that also taking into account temperature changes in silicon output?
Yes. Yes, that paper from Sandia, they evaluated various technologies, and they found that for most of them, I think thin films, if I remember correctly, were not on that nice range of accuracy, but the other ones were predicted well. And they compared different, like PVSys and SAM and some other in-house models.
And also the radiation accuracy now, is that for how many locations is that? There's thousands of areas in the United States alone.
Yeah, that is true. That was in a particular application. I guess the test was on Albuquerque. And they there's various models to model irradiance, so the Perez and all of those that I described.
So that's for one site?
That's for one particular site. And there's, on the radiation side of things, there's a lot of other studies of how close they are, and it really varies where you're at. That's why sometimes they suggest to use one model versus other, but there's no real consensus. That's true.
So if you have efficiency degradation due to whatever, maybe solarization, none of that's. So they fail badly over time, but they're pretty good like PV panels have.
Yeah, I mean, degradation is fairly predictable. I mean, grades are supposed to do 80% after 30 years or something of initial performance. So
That's not exactly true, because it's true over if you average over 20 years, but like if you look at the first 5 years, it's not a linear line. It's a double exponential in fact. So what you find is that for the first couple of years you would vastly predict your power production, and in 20 years you'd be doing it. But for the first 5 years you'd be way below what you thought you should get.
So one other question too is, so you have 2% variability in radiation, 3% for performance for one site. So have you thought of how this translate? You mentioned bankability. So what if, you want to place a facility in Seattle? So how are investors going to know how confident they should be about the performance based on something that occurred in Albuquerque? Have you thought about that?
So I am providing one validation for the visual modules.
Right.
I think there's a lot more that people are starting to do with their own field systems, and that will eventually converge now that we're establishing a framework to talk all in the same terms of bifaciality factor and bifacial gain. So definitely one project only will not provide people with that assurance that it will work.
So the bottom line is that there's still a lot of unknown. There's very limited site data, and predictability transfer to other locations is not very well established.
Yes. Yeah, so definitely we need to continue doing. So it's an area that needs more more of this research. And I think this puts a nice guide on how to go about this. The dissertation has a very standard section on how to predict the uncertainty, which is that accuracy of the measurements. So that can be followed up and applied other work.
By the way, if others have questions, feel free to ask so far during the presentation.
Yeah, there's also little note cards so you can write down stuff. Thank you. Okay. Any questions from the people online so far?
Keep going.
That was a no? No, okay. Okay, let's continue. Okay, so we had this bifacial gains for irradiance and for yield that we already saw. This shows on literature some of the experiments that have been done. And this, I guess, ties a little bit to Dr. Kostik's question. There is a widespread of bifacial gains reported or calculated, depending on the site, on the setup. Some are only one module, some are smaller arrays, some are bigger arrays. And the difference is quite high. It's like 6.4 difference in some of them on the prediction and the model. And that's what we're trying to improve. So talking about a little bit of the type of models, we're going to focus on this part for a little bit, okay? So talking about the irradiance models. Front irradiance, as I mentioned, it's pretty well modeled so far, understood, because usually you don't have the panels shading each other, usually. Now, rear irradiance, the panels are shading each other. Like, so depending on how you set them, the amount of light that reaches the back of the panel is going to vary. So you have the things of how high you set it from the ground, what tilt you use, what, I keep pointing at the thing, yes. What row you use, what spacing you use. That will change the amount of light that reaches the back of the panel and the distribution that it has. Other things, the weather will obviously affect. The number of rows that you have. If you only have one panel, it's going to perform super cool, right? Super great, right? But if you have a lot more, there's a lot more self-shading going on. So we have to model this, and we can use something very simple or something more complex, right? So on the simpler side of things, we have empirical models in which someone had an array, they measured the performance of panels and came up with a formula with some coefficients that you can use to predict how your system will perform. Prism Solar and SolarWare have come up with some equations of this, some fit to data that they have taken. Then we have view factor models. View factor models are geometrical models. PVSys uses this, and NREL has a bifacial view factor model, which you basically calculate how much of the sky you see from every part of the ground, and then how much of the ground you see from every part of the module. So it's geometry. And then we have Raytrace models, which are more complex. They're optical. You send rays, see where they bounce, where they reflect, where they get absorbed. And you calculate then the energy reaching the panels, or the radiance reaching the panels. And so we have one bifacial radiance available on GitHub. And we also developed one with the special characteristics that I'm going to briefly mention a little bit later. But these three that are on red are the ones that I've been working in for the past year and a half and helping develop. And the view factor model, just to give a little bit more detail on all of these three models. View factor model, it's related to et and do for people in optics. Yes, so yes, I get thumbs up. And we are dividing, to apply this, we are dividing the ground into segments, just the X segments, and the panel into segments or detectors, and calculating the irradiance from point to point. And walking through this, we have a segment. We calculate how much of the sky is not blocked by the panels. Then we see if that segment is shaded or if it gets direct sunlight. So we add that direct sunlight to that diffuse part that is collecting. So we add that. And then we calculate the front irradiance, which is the direct irradiance from the sun, and the ground contributions from the segments. So we do include this here. And on the back, we calculate the ground contribution from the segments and Fresnel reflections from the glasses on the back. So those are pretty much the 5 steps on every view factor model. Now, ray tracing, we can make very complex simulations, just like this one. This is just a picture. But we have a scene which we can say it can be as simple as just making boxes that are the modules. We can build the racks, we can make abstractions if we want to. But to all of the things that we build in that scene, we have to add material properties. We have to say, this is reflective, this is absorptive, how much? And any other characteristics that you can add to make the model more accurate, more resembling the physics. And then we have the sky. And the sky, we have to model how the sky is. The sky is our source. So we have to add source properties. So a little bit more on the construction. The Raytrace programs are usually like geometry programs. You can build a block, tilt it, move it, build another block, tilt it, move it. You can do more complex things like a tracking system with the torque tube and the two up, yeah, like on this on the left. Or even model every single cell with properties of glass and the electronics on the back and just build a scene the size that you want. And after you have your scene, what you do is you reverse ray trace. This is a property of the ray trace models that you go from the solar cell towards the sky. Why? Because you want to sample enough, accurately enough. And if you were throwing the rays from the sky, there was a very small chance that you will hit the solar cell. But if you throw it from the cell, you will hit the sky. So the sampling is greatly reduced by this. And on the sky, let's talk about the source now. The view factor models use isotropic, yes. Use anisotropic model, thank you. Anisotropic model, so that means that the diffuse light coming from every single angle is the same, right? So it's all the same type of blue. But we have models that we can use that can model the actual distribution of this light. Because the sky is not the same brightness or the same blueness everywhere. It's usually lighter near the sun. Can you tell where the sun is in here? Or will be. And also near the bands of the horizon, it has a different gradient. So we have models, for example, the Perez model is the one that I use a lot on this dissertation to do this. And when you're going into a simulation program, you usually want to discretize things. And we discretize it, in this case, in 145 patches. We could do 1,000 or 1,000,000 if we wanted, but there was a study by Robinson and Stone that proposed this that found that 145 patches was good enough for daylighting simulation and irradiance and gives an accurate description of the sky. So, yes?
When you're talking about your model for diffuse sky, are you saying that, are you suggesting that you're looking at the spectral composition of sunlight across the hemisphere, or are you looking just at total irradiance if you integrate the entire spectrum? So which one are you talking about?
Right now, I'm just talking about total irradiance. On the enhancements, I am going to present how I modified it to do this spectra. Yes.
So I have a question too. Is diffuse sky the same as, does it take a diffraction coefficient off the structures as well, or no? Because you guys talk about reflection, but when you have the metal structures, there's some
Reflection coefficient.
Yeah, of the structures, or I mean, does it account for
Well,
that? I mean, what do you think? So let's ask the candidate.
So it considers Fresnel reflections. I think in
Okay.
general, at least on Fred, to do diffraction simulations, you have to go a little bit more
Okay,
detail into what you're doing, into the
Okay.
material properties.
okay.
So I really don't know how it will do.
Well, I was even thinking about the nearby structures, you know, when you have the panels, and
Yes.
if a single panel is easy, but if you'll have some diffraction from the nearby
So
structures.
we'll have some reflection for sure.
Yeah.
So that it does consider that.
Okay.
So the rays get sent out in a 2 pi hemisphere, and they specify how many number of bounces they will have, or until which amount of energy they will just fade.
Okay.
And depending on the property, they will absorb some part and reflect. And for no reflection, you can put scattering too, which is pretty neat.
Okay.
So, yes. Okay. So this is the diffuse part. We also have to add the sun, which is a point source called emitted light. So we can add it as a point, or we can add the value of the sun irradiance to the patch where it's the closest at. The advantage is that you can do 2 sources or 1 source, which cuts a little bit on time. Right? Now, if we were to do a sky for a particular time, let's say 10 a.m. today, then and you want to model that for the whole year, you have to do 4,380 skies, simulations. All right, that's a little bit much. But the advantage of this is that you can actually accumulate the skies. You can add, for example, all the values for a day, that you only do 265 simulations. But you can add them for the whole month, that you have 12 simulations. Or you can add them for the whole year, every single hour. They just add, and you end up with a simulated yearly sky. You just run one simulation, and you know your yield output for the year. So this is cumulative sky. Let's talk a little bit about the enhancements. One enhancement was into this cumulative sky. We started working with tracking. So what we came up was creating skies based on the tracking angle. If we are tracking for, trackers have a maximum and minimum limit, let's say 45 to minus 45, and we're simulating every 5 degrees. So we're gonna find which hours the tracker is at those positions, and we're gonna add them to that particular sky. So we're gonna end up with a number of skies, in this case, from minus 45 to 45, every 5 degrees, that is 19 different skies. So we have to run 19 simulations. It's not terrible. 19 simulations where at each one our tracker is at a different position, right? If you take a photo of a thing that's moving, it looks static, right? So yeah, 19 of those. And we can do pretty neat things with the Raytrace and the Raytrace programs. We can model the tracking, and here we have a simulation of tracking panels. And on the right, we have the bifacial gain calculated for the whole center row and how it changes through the day. And we can see there's some edge effect, so it's a little bit higher near the edges because it's receiving more light, and other things. So we can do this with the Raytrace. Other cool things that we can do with the Raytrace is, let's see how this works in all of the world. So if you choose a particular setup, let's say at this height, this clearance, and you grab maps from the world from NASA, the database of the albedo. Albedo is reflectivity. I don't think I've mentioned that before. How reflective each part of, how reflective the Sahara is or things. And you also grab the weather from the satellites. Then you can predict what the bifacial gain will be for the whole world. And just using this, we get the 9% global average typical, maximum of 20. And this is not ideal. If you were to set up a bifacial plane, you will, with tracking, you probably really want to work on your reflectivity, right? So this is just grabbing what's naturally out there. And on the spectra, and this will answer Dr. Potter's question. So spectra is the contents of light, right? We've been talking about light as just a bulk thing of power, watts per meter square, but we have wavelengths in it, and each wavelength comes in different quantities, right? We have a lot of blue and red light that is on this range over here. And the direct and the diffuse light look different. The diffuse looks bluer, right? The sky is blue. So the scattering, it's a little bit bluer. It's also, if you look at the scale, a lot less power included. And there are programs, you can measure this with a spectrometer, or there are programs that can model this for you. So if we model, I model all of this for June 21st, just to show as an example. If we integrate the area under the curve, we can get what the irradiance, the total irradiance is, right? And that will give us the shape as the sun goes up, it reaches that 1,000 watts per meter square, which is the average, right? And the diffuse also goes up. Now, with the weather data that I've been talking about, the statistical, right? We see that it's not always as high as it should be, and there's some clouds coming in here, right? So one thing that we wanted to do was implement this weather data with the spectra into the sky model. So let's look at, for example, that particular time there. We have 930 watts per meter square and 111. This is weather data on diffuse. We can use the models that exist with that particular direct and diffuse value to make the sky. This is part of the Robinson, Stone, and the Perez all-weather model. And so we get up values for each of these patches of radiance of the light that they have. And if we have then this, we use the smarts to calculate the spectra. We normalize, we calculate what the irradiance is for that spectra, and we normalize it. So now we have a normalized spectra. And then we multiply this by the value of the patch, and then we get a distribution of spectra for that patch. And we can do the same that for diffuse. We know what the value of diffuse is for every single patch for one particular We have the spectra. We calculate what we integrate. We normalize. And then we multiply by the normalized value to get the shape of the spectra for that patch. And this is how we build the whole sky. And we can use this for things like doing a more detailed analysis of spectral properties of reflectivity of the material, or maybe put some holograms there, like on lab. And there's a section on the dissertation on that, although I think this is most what I'm going to talk about it right now. But it allows it to do that, this sky. Okay, let's talk about results. Okay, so in this part, we're going to focus on modeling. First, let's compare these models, right? Just a part of the models. This shows a comparison done with all of the softwares. With the same setup for Richmond, Virginia, same height, clearance, row to row. We just varied one parameter for all of them and came up with this. And what we can see overall is that there is a trend. Prism Solar is perhaps getting a little bit outdated now, but all of the other ones that are kept up, that have continued being modified, they are up to like a 3% of accuracy. This is irradiance. So that's not bad, that's terrible, this is good. People are a little bit excited that we're finally here. Every year there's a conference about bifacial modeling, and everyone was like, modeling. And this one's like, oh, we're getting there. I think we're getting there, so this is good. But one thing, though, is that we don't know where the real measurement is, right? We have precision on those measurements, but what is the accuracy? So we need to actually build the physical part and compare it to validate. So we built a testbed made of unistrut and aluminum panels, painted all in black, so to just absorb and reduce spurious reflections. And we built 3 of this, painted the roof ceiling of building an emerald white, and placed sensors on the middle row. And the sensors, 2 are facing forward, 4 are facing backward, so we can get a distribution, so how it looks along the slope of the panel. We also built a data logging system, which recorded the data for 4 months for the different setups. We kept each setup around 2 weeks or so. And it recorded data from the detectors, the irradiance sensors. And it had a solar panel, so it worked autonomically. So it didn't have to be plugged in or checked, it just recorded the data. So that was really cool. And for weather instruments, so for the input to the model, right, we need to know what the actual irradiance is. Besides measuring what the irradiance is, the result, right? So we didn't use weather data, statistical. We actually used data from the Solar Radiation Research Laboratory, which has a lot of sensors up to standard. So it's like the best data that we could have get. And luckily for us, it was right there. So 30 meters away. So the input data for this is excellent. Here are some preliminary results. We have the front measure and the front back. This is just 3 days just to show how the data looks like. I'd like to get a feel for that. So front model and measured with one of the programs. It matches pretty well. You can barely see the red and the orange, maybe some cloudy differences there. But on the diffuse, the measure and the model, the model is definitely undershooting. And we see this on the B factor a little bit sometimes, that it underpredicts. You had a question?
It was scratching.
So,
Scratching.
so your test setup, though, I mean, you have completely black surfaces. The PV modules generally have some clear areas. So
Yes.
what was the rationale for not just using modules if you wanted to accurately compare? It's introducing some error.
Yes. So we are comparing to the models. The models, you can set up what transmissivity you have in the cells, so your packaging factor. So we set that to 0.
Oh, okay. I see.
But yeah, in general, I guess the point of the test was that we could change the height, we could change the spacing, and that's usually not common on fields because moving like whole array. This was a mock-up for a 10 panels row. So moving all of that requires a lot more operation maintenance issues. So this was a good way to test for that.
So, let's see, I'm just
trying to understand your plot here a little bit better. So you have model, view factor, and measured. So they're sort of close. And the red curve is the
Measure and model, but for the front. So this is comparing the front irradiance and the rear irradiance. Yeah. Yes.
What type of sensors, what are you using to measure?
The word IMT reference cells, SI01 something. So they have a temperature sensor internal, so they actually calibrate for temperature too. So they're pretty much standard on the field.
Sorry, I had a question on the previous slide.
Yes.
Did you calculate the error for front side and the back side? And if yes, how much was that?
I did, and it's on the paper. I don't remember it right now. I'm sorry. I
Okay.
think it was something like 2.3%.
Okay, cool. I will take a look at the paper.
Please check. I know I brought it on the journal. I apologize.
Okay.
Okay, so those results were published in a journal recently, on the Journal of Photovoltaics, and this compare for different heights. So when we move this testbed up, and when we space this testbed, the row-to-row spacing on the right. And we are comparing the view factor and the radiance model from NREL. And the circles are the measurements that we took, and the uncertainty of the measurements. Okay, so in general, the measurements, the models fall between the uncertainty of the measurements, which is good. So this helps us say, okay, we're close. At some points, the view factor underpredicts. At some points, the Raytrace goes a little bit high. And these are things that we still need to continue researching or polishing. On the profile, how the profile looks on the back of the panels. And this is just to prove that when we have the panels at higher clearances, there's more uniformity, right? And we want that usually in panels, the same irradiance all over. When they're a little bit lower, there's a little bit more of a difference, and that will affect their performance later. Okay, so on the last 10 minutes that I have, let's talk about the bifacial gain. This equation that we already presented, right? We compare bifacial and monofacial panels a lot of times just by dividing the power. But what if we have like a really good bifacial panel and a really bad monofacial panel, right? Then we're obviously going to have a lot of bifacial gain. That's supposed to be a really bad monofacial. Yeah, anyway. Now, one thing that we usually do is use the performance ratio. So we make sure that at least the panels we normalize to the panel value, right? So we have 225 watt panel versus another 225 watt panel, or we normalize. But even if we're using the same panel, the same 225 watt panel, right? The bifacial gain that we measure will be different. Why? Because depending on the technology, depending on the panel, there's a lot of things that go into that performance, into that output. And a lot of things like different temperature coefficients, different low light dependence, that's very important. How we mount them, some have frames, some don't. And all of that besides the bifaciality, the fact that our panel accepts light from both sides. And we care about the bifaciality because we're modeling irradiance, right? So to actually focus on this bifaciality, we can apply a correction factor. This correction factor, it's basically calculating the front performance for the monofacial and the bifacial and applying that correction. And in that front performance calculation, all of those factors, that we have an accurate temperature coefficient and module parameters, then that will take care of that difference in technologies. For example, we apply this to a tracking system on Klamath, Oregon, which is on that little spot up there. We had two fields, one monofacial and one bifacial side by side, so same albedo, same clearance height, same row-to-row spacing. They were the same power, 100 kilowatts versus 100 kilowatts. The Silfab is a HIT technology, and the Trina was a multicrystalline technology. So there's difference on the technology itself already there. So we apply just a traditional bifacial gain of just dividing the production of the bifacial to the monofacial. We come with this plot here. We come with a value of 9.4%. Or bifacial panels are 9.4% better than the monofacials. However, again, as we mentioned, there's a lot going into that 9.4. And if we apply that correction factor, we find out that the bifacial gain due to bifaciality is 7%. And the other is just because we're using a better technology. Okay. So validating this, knowing this output, this using this bifacial yield model with the correction factor can help us compare more directly to the irradiance model, because now we're talking bifacial gain due to bifaciality versus the irradiance gain. And we see that that is actually very close. If we model the irradiance gain, it's 6.7 versus 7%. There's a couple odd months out there because there was snow. And the snow first helped us because snow is shiny and the power increased a lot. But then there was too much snow and there was no power, so that was January. So on conclusion, I had just presented the implementation of a publicly available view factor model. I described how the view factor model works, and I helped code that, and that's on GitHub. You can use it if you want, yes. And this model has actually already been implemented on SAM. So all of this work has helped towards that. I just presented the characterization of the model, so a comparison of all the models in a similar same scenario setup. There was the design of a scale test bed and all of the measurements taken from that, and particularly the uncertainty, which tells us what accuracy, if we are close or not on the modeling. I also presented development of a methodology to evaluate the bifacial gain of the single axis tracking. So that modification to the sky and to the software to be able to model when we are tracking the sun. We have a formulation of a framework to quantify the bifacial gain. So this last part with the correction factor, and that's very important going forward on the field, I think, so that we can trust the values that we're being given. We have the integration of the sky diffuse model, the spectra, to generate the irradiance. And a tool also developed for the use and evaluation of the holograms and with bifacials on our lab for that. And finally, I guess I didn't really talk about this, but there's some, those of you who were in the Master's Defense heard about the holographic cap and the bifacial, which is basically putting a hologram on top of a bifacial panel. Okay. Acknowledgements, thank you very much to my advisor that's been very patient and has also demanded a lot from me, and I appreciate that. It's made this work a lot more deep and better because of that. Previous students, thank you, Stella. And everybody else on that list, I'm very, very grateful. Yes. Funding sources kind of helped me the first years here. Then Quest has been a big role both in mentoring and in funding this. And Real this last year, and a lot of travel grants, because I traveled a lot this year to talk about this research and get the word out there. And special thanks to Chris and Josh. They were co-authors, and they also went through the dissertation and offer really good feedback. I marked actually with a star all the people that read the dissertation, and I'm great. Thank you for doing that. And the Enroll Media group for helping build the testbed and everything else. And special thanks to my mom that's watching, and my dad that's also watching, and to my dissertation writing sister in arms, Kelsey. She just defended 2 weeks ago, and we wrote together for months and hours, and the amount of coffee is unbelievable. Thank you to my aunt too, and my sharing squad, which provided food and many hours of encouragement. I also wanted to give a shout out to the counseling and psychiatry services at school, because they have a women's group that is excellent, and they give a lot of life and PhD advice, and the writing skills improvement. Dr. Kote, thank you. It was really good to have the help of the writing group. Please, if you're still in school, please go there, please. We are Women in Optics. That's all my friends. Thank you, with pom-poms. I guess I should show that. And all my wonderful friends and mentors. Thank you. So, questions?
There's a question behind you, Ray.
Oh,
Yes.
So, would you say that the bifacial use will override cost of implementation? Like, is it worth it to use bifacial instead of monofacial?
There's some economic studies on that, yes. So the answer is yes, it makes sense.
What's the title of your paper?
Model and validation of, no, I have a slide for that. If you want to bear with me. All of the backup slides. This one's. So those two first ones.